Okay, thank you very much for the introduction, Tristan. And today I will discuss my joint work with Bongjong Choi and Toti Daskala and Bob and Natasha Sesam about the classification of bubble-shaped ovals in R4. Okay, this is a topic related to the mean curvature flow. So let me first introduce what is mean curvature flow. Here first, I consider mean curvature flow in Euclidean space. So in this setting, the mean curvature flow is a family of embedded hypersurfaces into Euclidean space, and whose evolution equation is given by this equation, and its moving velocity vector is given by the mean curvature vector. Okay. More intuitively, let us have a look at this picture. And the initial surface is a dumbbell-shaped surface, and along the evolution of mean curvature flow, and at this point, you will meet a singularity. And in this picture, it flows through the singularity and breaks up to two pieces, and then shrink to two round points. And so, if we look at this singularity, and we use we zoom in the singularity, and we will find out it's a 1R factor cylinder. And in this case, and we call this type of singularity as a neck singularity. And so natural question is, can we flow through the this, for instance, this neck type of singularity? And the recent breakthrough by Daimler and Kleiner, and then together with Bob's work and Bob and his collaborators' work, and shows that in this picture it's indeed okay, and we can uniquely flow through this singularity. I will come back this later. And so why do we care about the mean curvature flow? And first of all, and it has many similarities as Ricci flow, and we know that Ricci flow has many applications in geometry and topology. And so this is the extrinsic flow, and so we wonder if we can use mean curvature flow to solve the geometry or topological problem. And some related problems, the first one is the smooth Schuflines problem. Like, does every smooth three sphere bound a standard smooth four ball? Okay. And a work of Weinstein and Professor Lu Wang, and also Chodo, Choi, Mantelidis, and Schultz, and they studied the this Schuflines problem by studying the following problem: classification of the low entropy hypersurfaces. Okay, entropy is some Gaussian weighted integral, and its value is less than its value on the cylinder. And then another related topological problem is Smell conjecture. It asks to study the moduli space of embedded spheres into Euclidean space. Moduli is diffeomorphism groups. And so question could be if this this space is contractible, or other maybe other topological properties like connectedness. And also from the PDE point of view, that we can ask if the flow can be uniquely through the singularities. Okay, this is some background. And so as many long linear PDEs and mean curvature flow, it has singularities. What is the meaning of singularity? Okay, singularity here means that at a singular time, and its second fundamental form will blow up. And to apply the mean curvature flow, the key is to classify and understand its singularities. And let me first recall some classical examples results about the classification of singularities of mean curvature flow. And first of all, and it belongs Grayson, and they showed that he showed that the curve shortening flow, which is the mean curvature flow in plane, okay, and always converges to a round point. Here, the round point means that if we zoom in, and we will get a circle in the, okay. The second one is, in higher dimension, and belongs Huiscan. And if we assume that the initial surface is strictly convex, smooth surface, then along the mean curvature flow, it will converge to a round point with infinite time. Still, it means that we can zoom in and we get a sphere. Okay. So in general, if we don't assume convexity, and how do we study the more general singularities? And so it depends. It relies on the how do we do the zooming and the blowing up. Okay. So mean pressure flow, it has the parabolic symmetry, rescaling symmetry. It means that if M satisfies the mean pressure flow, then we can parabolically dilate the flow. It means that the space is dilated by lambda and the time is dilated by the lambda square. Then the dilated flow is still the mean pressure flow, satisfies the mean pressure flow equation. Yes. And
is this all in Euclidean space?
Yes, I'm studying Euclidean space. Okay. Yeah. So so using the this parabolic rescaling, and we can define the what is the blow up. Okay. Specifically, they are called the tangent flows and limit flows. And let us consider a sequence of numbers going to infinity, okay, lambda I. Then if we fix the space-time center x0, t0, and we translate it to this center, and then we dilate it by this parabolic dilate it by this lambda I. And if the limit exists, when we limit exists, and we call it as a tangent flow at this point, okay? But more general, okay, if we want to study the neighborhood of the singularity, okay, and we need to consider more general flows, limit flow, and the limit flow, and in the limit flow setting, and its definition varies. The space-time points can varies, okay, and if the limit exists, and we call this as limit flow. So okay, then another tool for the blowing up is the Huysken's monotonicity formula. Okay. Oh, sorry.
I have a question.
Okay.
Maybe this is too long a question, but why do we do the parabolic rescaling?
Oh, maybe we can consider a minimal surface first. Okay. For a minimal surface, and if you have some singularity, and you move the singularity to origin and dilate it, and you will see the singularity structure of minimal surface. But minimal surface is scaling invariant, right? And so the point why we do the parabolic rescaling is because of the symmetry. And because the mean pressure flow, if you parabolically dilate it, and it's still the mean pressure flow, so it doesn't change the equation. So you can zoom in and see the picture. Okay, zoom in like in the first picture here, right? And if you zoom in and do the dilation at this point, okay, then you will see a 1 R factor cylinder, just the cylinder. Okay, is this clear too? Okay. Okay, so another useful tool is Huysken's monotonicity formula. And let us consider this Gaussian weighted integral. Okay, we differentiate it, and then it's negative, non-positive. And so a more important thing is the quantity in this absolute value. And this absolute, basically my guess is this monotonicity formula is to find out this quantity. And the quantity, for example, if this quantity vanishes, it has some examples like the shrinking cylinders and shrinking spheres. Okay, and so using Huysken's monotonicity formula, and one can show that the tangent flows and the limit flows. Okay, so they always exist in the weak sense. And moreover, if we consider the tangent flow, okay, and it's always self-similarly shrinking, it means that it's just the square root minus square root absolute value t times its minus 1 slice. And the minus 1 slice, and it satisfies this shrinker equation. Okay. Examples of shrinkers include this is flat case and sphere, and also the some R factor times some sphere factor and the general cylinder, and also some asymptotically conical shrinkers. I think Jacob is an expert in this conical shrinkers. And so another issue is that in the previous picture and in the previous slides, and this tangent flow, for instance, and it can be, in the weak sense, and it may converge in the variable sense to higher multiplicity. And so if we consider the specific type of tangent flow, if the tangent flow at singularity is multiplicity 1 cylinder, then we call this cylinder as a cylindrical singularity. When there is only 1 R factor, it's called as next singularity. When there are 2 R factors, and it's called as bubble shaped singularities. Okay, and coding minicosis, they conjectured that these cylindrical singularities, they are generic. And in the surface into R3 case and Baumler and Kleiner and recently proved that, okay, this must, I mean, this must be multiplicity one. And also the, I mean, these cylindrical singularities are generic, okay. Okay. However, if we, I mean, the shrinker, I mean, self-shrinking solutions, the tangent flows can be analyzed by self-shrinking solutions, but limit flows, and how do we analyze limit flows? The more general consideration is to consider to put them into the ancient solutions class, and to study the classification of ancient solutions. And it's a parabolic type of Bornstein problem. So what is the meaning of ancient solutions? Ancient solution mixture flow is called ancient solution if it is defined for all the time from negative infinity to some time which could be positive infinity. And because of we do the tangent flows and limit flows, we do it by the parabolic rescaling. So it's I mean its lifespan is from negative infinity. So they are the ancient solutions. Some more concrete examples I mean of ancient solutions. They are called non-collapsed and collapsed. Maybe I first explain what is collapsed solution. Okay. So collapsed solution, okay, this is two pictures of collapsed solutions. The first solution is a translating solution, downward translating, and it's collapsed, it's convex, but it's still collapsed. The collapse means that intuitively in this picture, it means that it's restricted into a slab. And so it does not, it's not the entire solution, for instance, entire solution of the whole Euclidean space, and it does not sweep out the whole space. And in the second picture, and it's a pancake solution, is also restricted into a slab with finite height, okay? And the backward evolution, and it will fill in this slab, but it will not sweep out the whole space, okay?
So when you were defining the solution, they were defined for arbitrary t, the most negative positive sphere, but going find that or you're about to shrinking solution, like
There's only capital T, right? Mine is going to be capital T.
Yeah, capital T. Yeah, this is the definition of.
sorry.
Yeah. Okay. So collapsed means, I mean, although they could be convex, but it's basically not that much. I mean, does not sweep out the whole space. So what is okay? So what is non-collapsed solution? Why do you care about non-collapsed solution? A non-collapsed solution, they naturally appear in the mean convex mixture flow. And White and he pioneered and established the theory and for the mean convex mixture flow. Mean convex means the mean curvature is non-negative. And also later, Andrews, I mean, Haushofer, Kleiner, and Shen Wang, they also made contributions in this direction. So as I said that initially that we can classify the convex solution. Then we consider how to classify the mean convex, I mean, singularity models. Okay. And so White, Haushofer, Kleiner, and they obtained the following results. The blow-up singularity models of mean convex mixture flow are always smooth convex, ancient, and non-collapsed. What is the meaning of non-collapsed? Non-collapsed means that at each point in the slice, okay, space-time slice, you can always attach interior and exterior ball whose radius at least some uniform constant alpha and over the mean curvature. Okay, it's more like a quantitative. I mean, together with the ancient, I mean, convex this condition, and then it's more like a quantitative characterization of how convex it is. Okay, so here are some examples of ancient non-collapsed solutions. And the first picture is a static plane. The second picture is, I mean, second and third. Basically, the first line are generalized cylinders, and the third line, the second line, and the first picture is a translating ball. It's almost like a paraboloid, and also when it translates, it will sweep out the whole space. And the last picture is called as Asian oval. And in this picture, the Asian oval in the middle, and it looks like a cylinder, and in the tips, and it looks like glued the two translating ball. But actually, these two pictures in higher dimension, they are not the, I mean, I will show that they are actually not the only examples. Okay, there are more examples. Okay. So, by pioneer works of Anglin, Daskalopoulos, and Sesam, and Brandon Choi and Choi Hassover, Perskovich and White, and they basically have made it clear that the next type of singularity, okay, they are classified into the round shrinking cylinder, this translating both solid tone solution, and also the Asian oval solutions. Okay, and in the R3 case, and basically they use this classification, and they obtained that the mean convex neighborhood conjecture, and also uniquely flowing through the next singularity. Okay, this. But recently, together with Baumler and Kleiner, their results, and for initial surface, okay, together with this work and with the initial surface spheres surface and the well-postness of mixture flow is proved. Okay, and in higher dimensions, okay, and Choi, Hassover, Perskovich, and White, they obtained the uniqueness of mixture flow flowing through the next singularity. It's just one R factor cylinder. Okay. Okay, but how about I mean, if we have more R factor cylinder? Okay, so then we consider the so-called ancient asymptotically cylindrical flows. An ancient asymptotically cylindrical flow is basically the tangent flow at negative infinity. What is a shrinking cylinder? What is the meaning of tangent flow at negative infinity? And look at the okay, it's Asian solution, and here I mean different from the tangent flow, and we will scale it by lambda, but lambda goes to 0, and if the limit is a self-shrinking cylinder, and we call it as Asian asymptotically cylindrical flow, and also Coding Minkowski, they actually proved that this I mean, this is unique. It doesn't depend on, actually, usually we will choose a lambda I, but it doesn't depend on the choice of the sequence of lambda I. And so in order to solve the higher dimensional mean convex neighborhood conjecture, and we need to study the classification of ancient asymptotically cylindrical flow. What is the mean convex neighborhood conjecture? It says that asks, okay, the mean curvature is always positive in some space-time neighborhoods of cylindrical singularities. If we meet a cylindrical singularity, then in a parabolic neighborhood, it should be, I mean, the mean curvature should be non-negative. And the proof of this conjecture is basically by blowing up, and I mean, if it doesn't hold, you do the blowing up, and you get some Asian solutions. And if you know the Asian solutions classification, and you get some contradiction. And then the question reduces how to classify what is the full classification of general Asian asymptotically cylindrical flows, or more narrowly, if we restrict it into the mean convex world, and we are asking the Asian non-collapsed classification of Asian non-collapsed mean curvature flows. And what is the difficulty? The difficulty is that unlike the previous picture, and when there are two more R factor, okay, then there are actually more examples which is not like along the spherical direction or rotationally symmetric. I mean, I mean along the RK factor, and it's not always rotationally symmetric. I will show the example. Okay. So let us have a look at the non-compact case. Okay. In the non-compact case, and we look at let us have a look at the picture in R4. Okay. In the non-compact case, and we have a self-translating solution, and it's Asian non-collapse, and each slice, okay, each level set looks like a 2D oval, okay, looks like has asymptotic behavior like a 2D oval, and but it's not, I mean, fully rotational symmetric along this direction, and its shape is actually controlled by the tip curvature ratio here, okay. And if some tip curvature vanishes, and it will split off line, okay. And I mean, Hoffman, Emmanuel, Martin, White, they they showed the existence of such families of ancient non-collapsed these both solitones, and okay, they only have the reflection symmetry times the rotational symmetry. And later, and Choi has research, and they showed that okay, every Asian non-collapsible translator in the four-dimensional space up to the rigid motion and scaling, they are basically interpolating by this R times 2D ball to the round 3D ball, and by this picture, okay, HIMW oval balls, okay. And this is the non-compact case, okay. How about the compact case? Let me give a formal definition of Asian oval. Sorry, it's late. Okay, Asian oval is actually ancient non-collapsed, non-self-similar. It's not self-translating, also not self-shrinking, compact miniature flow. Okay, below is a picture of Asian oval I have shown, but there are more examples. Okay. And let me first discuss some uniqueness result. Okay, and White House research, and they show the existence of this type of OK times O n plus 1 minus k symmetric Asian ovals. Okay, and also Angenon, Daskalopoulos, and Cesium, and they conjectured that this type of ovals are unique. And later, in my joint work with Bob, and we proved that they are actually unique up to the rigid motion and scaling. And more generally, and we use this. I mean, this rotational product rotational symmetric ovals rigidity, and to obtain the full classification of the OK times O n plus 1 minus k symmetric Asian non-collapsed solutions. They are either the sphere or the cylinders flip or flipping the coordinates or the unique Asian ovals, okay, constructed by White House and And but I want to say that there are actually more examples, okay. So in my joint work with Bob, and we showed that still for simplicity, we restrict the picture into R4. Actually, in R4, and we have one parameter family of such geometrically distinct the Asian ovals, which only has this Z2 times the O2 symmetry. Okay, and what is the shape of this picture? What is the shape of this Asian ovals? Okay, actually, because it has O2 symmetry along the last two coordinates. Okay, so we can reduce the picture from R4 to R3. And in the R3 slice, and it looks like ellipsoids. And so basically, I mean, its shape is controlled, okay, by the like X1 axis this width over the X2 axis is width ratio, okay, the width ratio. If the width ratio is 1, and it's the unique O2 times O2 symmetric Asian oval. More generally, and it only has this Z22 times O2 symmetry. Okay. And the construction is basically we start consider the ellipsoids, and we probably time shift and dilate the flow, and I mean with some conditions like as the flow extend at time 0, and also satisfy some I mean entropy equation, and the right hand side is basically the entropy of S1, S2 average. Okay, and if we take the subsequence, and if the subsequence limit exists, and we collect them together, and this is the Asian oval class we have constructed, and I mean it's distinct. They are. I mean, its non-uniqueness is proved by some degree argument. And so we have constructed examples. Then the natural questions are all the Asian ovals. Okay, are they in our class we constructed? Okay, so let us have a look at the general steps to classify the ancient non-collapsed flows, or more general non-ancient asymptotic cylindrical flows. The first step, we can regard it as a Morse flow. Okay, classify the Morse flow and infinite dimensional Morse flow. And the first step is to prove the uniqueness of backward limit. Okay. And this step is basically the by code the uniqueness of cylindrical tangent flows. Okay, and the second step is that we need to analyze how does this flow backwardly close to the critical points, these cylindrical shrinkers. Okay, and also to study its symmetrical behavior. Then the next step is that okay, and like you have two ovals, and you want to they are in different position, and you need to use some symmetry and to first fix them into the same position. And so we need to fix some symmetry. And the only freedom we get is the freedom, I mean, the parameter which controls its shape, okay, geometric shape. And in the last step, and we need to use the asymptotics in step 2, and to upgrade the asymptotic to rigidity or the classification. And also the last freedom will give the moduli to a coordinates map to the moduli space. Okay. And let us have a look at the setup. Okay. So we assume that the MT and is the Asian asymptotically cylindrical flow, and its tangent flow at negative infinity is the unique cylinder. Okay, this is just by the definition of Asian asymptotically cylindrical flow. And because of this setup, and we can do the renormalized flow because this cylinder and depends on T, and after we renormalize it, and so it's close to a fixed cylinder. Okay, we kill the absolute value of T. And we can write the flow as the fixed cylinder graph of some function, profile function U, okay, and in some graphical radius range, okay, and so we can translate the mixture flow to to the evolution equation of this profile function U, okay. And the evolution equation of profile function U is asymptotic expansion is the first linear term is governed by this Ornstein-Uhlenbeck operator, okay? And the second term is some quadratic term, and the higher order terms. And so if we forget that these higher order terms, and it's basically some, maybe the easiest type of nonlinear Heat equation here, okay? And this is the toy model, okay, for us to study asymptotics. So in the 4-dimensional case, and in my joint work with Bob, and we basically proved the following theorem, but in the Asian non-collapsed setting, and later in my joint work with Zhu, we removed this non-collapsing condition and generalized to all the conditions. The following theorem is called as spectral quantization. It says that, okay, the asymptotic behavior, okay, of this Asian asymptotic cylindrical flow, okay, it's a profile function. If we multiply this absolute value of tau, and it looks like a quadratic polynomial. The quadratic polynomial is governed by this constant matrix Q, and the constant matrix Q is a symmetrical matrix, and whose eigenvalues are either 0 or is this negative number, okay? And what is the meaning? It says that asymptotically either this is flat or it's inward quadratic banding if along the negative eigenvalue direction, okay? So this matrix Q plays an important role in the classification problem. We call it as a cylindrical matrix. And remember that in this theorem, and we don't have non-collapsing condition. But for simplicity, and we will first as I said, that the classification has 4 steps, and in the later 2 steps from now, and we will add this non-collapsing condition and to study the classification problem. Okay. And for instance, in the R4 case, and there are only the matrix Q has only rank 0, rank 1, or rank 2. Okay, and so we can split the classification into the 3 cases. Okay, and the most tricky part is actually when the rank is in the intermediate rank is okay. But let me discuss when the rank has 4 rank. Okay, or degenerate rank. If the matrix Q, if the Asian non-collapsed flow, okay, it has cylindrical matrix Q with 4 rank, say it's 4 rank K, which is the RK factor, okay, agrees with the RK factor of the cylinder, and we call it as a K oval, okay. The natural, back to our question, and we're asking if all the Asian ovals belong to what the examples we constructed. So we can first ask the question if we can classify K oval, then we ask if all the Asian ovals are K oval. So if So here's a question. Okay, any ancient oval with this RK factor cylinder as tangent flow at negative infinity, and is it K oval? Okay. Okay, and in in the R4 case, basically, if this is true, okay, it's R4 case. This is basically equivalent to the classification of rank 1 case. Okay. And so let me discuss in R4 case, and if the rank is the rank for rank 2, okay. Okay, or maybe let me first discuss a bit of the vanishing rank case. Okay, and in the vanishing rank case, and okay, then the flow is actually either a round shrinking cylinder or some RK minus 1 factor times the n plus 1 minus k dimensional round translating ball, and it's basically obtained by splitting of 11 lines. And after splitting of the 11 lines, we reduce the, we have 2 convexity, and about the non-compact, then we use the Brandel and Choi, their classification of 2 convex non-collapsed solutions. But this is the easier part, and the more difficult part, let me discuss my drawing work, which is the title, sorry, it's too slow. And my drawing work is Meng Choi and Toti Descalabres and Bob and Natasha Sensen. And we proved the following theorem, that any 2 oval, also we call it a bubble shaped oval, another name, in R4, up to scaling and rigid motion, is either the O2 times O2 symmetric oval, okay, constructed by White, Hoscover, and Hoskovich, or they belong to the one parameter family of one parameter family of the ovals we have constructed. Okay. And moreover, if the we should say that if the rank 1 is, result is classified, and then its moduli space quotient quotient the Z2 symmetry, and it's a half interval. Okay. So as I said that because the oval, okay, the oval we in the asymptotics, and we basically we only studied the parabolic region, which is finite.
Sorry, can I forgot. So K oval means it's rank K, it's full rank.
Yeah, but in my case, we discussed R4, so it's rank 2, and the 2 agrees with R2 factor. Basically, it's R2 times S1.
So you're fixing the K for the
yeah
cylinder, and then for that K, Q is a K by K.
Yes. Yeah. The more difficult is like if it's R2 times S1, then if rank 1, okay, it's more difficult. So, and think about the oval, okay? The asymptotics, basically in the previous spectral quantization, it only discussed in the basically note. The oval has it will until the tip, right? And until the tip. Very small picture. Okay. Okay. Basically, in the previous spectral quantization, we only studied the asymptotics in this region, but in order to get the rigidity or classification, we have to extend the asymptotics from this region until the tip. Okay. Okay. Sorry. Then so in my joint work with Drew, and we studied the asymptotics of these 2 for instance, these 2 oval. Okay. And the 2 oval, they are actually compact and SO2 symmetric, and it has the following unique abstract asymptotics in the parabolic region. This is basically what we studied. It's basically equivalent to the spectral quantization with 4 rank 2, and then in the intermediate region, and it's basically, what is the meaning of intermediate region? Intermediate region is basically, it says that it's away from the tip, a bit away from the tip. And if we renormalize it a bit, and we will obtain that its asymptotics basically looks like ellipsoid. Ellipsoid, if we square both sides, and it looks like a ellipsoid. Okay, like along the height along the what is that? The height along the rotational symmetric direction is this square 2, I think. Okay. Then in the tip region, and after we rescale it and do blow up, and we will see some R factor times times the 2D oval, 2D translating ball. And this, then we obtain the full asymptotics of this 2 oval. Then the question is, how do we upgrade this asymptotics to the rigidity? As I said that this is step 2, but we need to go to step 3, and we have given any oval, and we want to classify it to the example class we have constructed, and we have to, I mean, if even their shape are the same, but we need to move it to the same place and to show that its difference of the profile function actually vanishes. Okay. So how do we study it? And we need to study the basically the, I mean, we have a toy model, and the linear term is given by this linear, right? This Einstein-Uhlenbeck operator. If we study this Gaussian weighted space, then the Einstein-Uhlenbeck operator, it has the Fourier mode decomposition, and its positive mode is actually spanned by this 1, y1, and y2. This 1 and its geometric meaning is given by this time shift, and the y2, y1, and y2 is given by the translating in this R2 plane, and the neutral mode is spanned by this quadratic polynomial. And basically, you can think about this. I mean, it's inward quadratic bending. But the last, this mixed term is basically given by this rotation. And the sum of these first two quadratic polynomial, I mean, like y normal square minus 4 is governed by this scaling, okay, parabolic scaling. So, and by I mean, ODE analysis of Maurer-Zeg ODE lemma, and we can show that, okay, the profile function, I mean, is evolution only governed by this, dominated by this neutral mode projection, or the and the positive mode projection. Okay. And if we look at the oval class we have constructed, because we started from some ellipsoid, it automatically has this reflection Z22 symmetry, right? And then by the, if it automatically has this Z22 symmetry, and this term scaled, and only this 1 and this y1 square minus 2, y2 square minus 2, the dominant. Okay. Okay. So I mean, as I said, that we need to make the symmetric grids, and so here, and we consider the following equation, that the projection of this profile function onto the mode 1, and also the projection I mean, to this y norm square minus 4. Basically, if this vanishes, and it agrees with the symmetric oval. Okay. And so we need to for any oval, and we need to find the good parameter beta and gamma such that this equation holds. But because later we need to prove the, I mean, we need to establish some, I mean, coordinates, and I mean, to the moduli problem, right? And the coordinates has to be like continuous, right? And also surjectivity, and we have to require the continuity, right, to prove surjectivity. And for the so, but however, you really, one of the difficulty is that this actually doesn't, I mean, have global continuity. You cannot say that beta and gamma, the scaling parameter gamma and the time shift parameter beta, and they depends on the flow continuously. But luckily, and we can do the, I mean, Jacobian estimates, and locally we can choose the continuous branch. Okay. So the Jacobian estimate says that this map is Jacobian is not, I mean, it's not generate. Okay. And as I said that if we use time shift to fix the time shift to and the scaling, and we basically kill the this eigenfunction 1 and y norm square minus 4, but there's still a freedom. Freedom is the so-called spectral width ratio. It's different from the geometrical width ratio. The geometrical width ratio is given by the width. Okay. So this is the last freedom which controls the shape of these ovals. Okay. And using the above Jacobian estimates and the continuity argument, we can basically show that this map is, I mean, basically is locally surjective. Okay, it's surjective. So later we will use this map, spectral map, to establish some coordinates to the moduli space. And so basically we showed that the existence of prescribed spectral width ratio given any number close to 1, and basically we can find the 2 oval we have, which is in the class we have constructed up to some, I mean, rescaling and recentering. Okay, it's mapped to the given number. Okay, it's a surjectivity. And so if we have surjectivity, and basically we can agree all the given oval, and we can find another oval such that, I mean, also use the symmetry, and we can make that all the positive mode and all the neutral mode, and they agree, but there are some negative mode which is higher order. I mean, basically it's higher order terms. So the question is, so this basically we have this proposition is that we can match the positive and neutral mode, but how about the other modes? And can we use these two modes agreement? The gray and implies the rigidity, uniqueness. Actually, yes. And so we can upgrade upgrade the sharp symptotics to the following spectral uniqueness. It says that, okay, basically it says that if their profile functions after the scaling and after recentering, and their modes, if the modes agrees, okay, the positive mode and neutral mode agrees, then they are actually the same. Okay. And how do we do that? And we need to use asymptotics. And basically, the intermediate region asymptotics tells you that if this is a profile function of some, I mean, basically we need to prove that the two profile functions, their difference vanishes. Okay. And so we study the evolution equation of this difference of profile function and fix someone. And if it is above some 2 theta region, and this is basically agrees with the intermediate region. And if it is below the L over the square root the absolute value tau, and its behavior looks like a bow solitone times R factor. Okay. And but the missing point is that if we want to upgrade the asymptotics to rigidity, and we have some missing asymptotics, which is the in between. Okay, this region is called the Kohler region. Okay, so so basically we need to do the energy estimates in different regions, and how to deal with this Kohler region. It's basically because we have certain type of monotonicity. So if we have the asymptotics into this region and this region, and we can use some type of asymptotic monotonicity to interpolate the asymptotics in between. And so it's related to the following proposition. Okay, and actually if there's only one R factor, and I will explain later. Okay, let us consider this profile function square, and okay, and so we study the Hessian, okay, but it's the intrinsic Hessian, okay, intrinsic Hessian, and also we act it on the vector field perpendicular to the last two coordinates plane is rotation vector field, and it's almost negative definite. This is the error term, okay, and so using this we have a Hessian second order estimates. Then we basically can get the first order derivative estimates is like almost monotonicity. Okay. So the question is, okay, so the difference from like argument das calculus and CSM, and like if there's only neg type of asymptotics, and they consider the extrinsic, this type of extrinsic, also this is non-positive. Okay, but here we have to consider the intrinsic version. Okay, and the proof is basically motivated by some tensor maximal principle, and we consider the tensor, and I mean we need to get good sign to apply the maximal principle, and finally, and we proved that I mean the spectral map and its surjectivity and injectivity, and so we can, I mean, we can obtain the classification, and also this surjectivity and injectivity gives the local coordinates, and also the surjectivity, it also implies the connectedness, and using the one-dimensional manifolds classification, and we can prove that I mean the modular space quotient, the Z2 symmetry is homomorphic to this half interval. And so in the end, I also want to discuss a bit about the higher dimensional case. And so in higher dimensional case, and I'm working with Beng Zhong Choi and Jinze Zhu, and we studied the higher dimensional case classification. And one of the key difference is that this does not hold in higher dimension. Okay, for the general K ovals. Okay, we need to modify it. Okay, this does not hold, and it's kind of very tricky part. And other part is actually this is a more tricky part, and this theorem also, because here we basically used the how one proved the intermediate one-dimensional intermediate value theorem, and the technique does, I mean, entire dimension is should be some degree argument, but it has some problem. Also, I mean, basically, I'm saying that this surjectivity and also this Hessian estimates doesn't, I mean, aren't trivial. And so let me point out some future possible problems. And the first question is, I mean, in the classification of, I mean, higher dimensional case is how about the classification? And even more tricky thing is, I think the intermediate rank case, and if the dimension will be very high, I think there will be some, I mean, examples, okay, which is different. And the other thing is, I mean, to prove that the mean convex neighborhood conjecture, we cannot assume that the convexity is expected to be the conclusion. Okay, so how to, if we remove the non-collapsing condition, how do we go the step 3 and step 4? Okay. And use it to prove the uniqueness of flowing through the cylindrical singularity. And another question is to topological problem. If we have the classification, like in R4, could we use it to prove if we meet our flow meets some bubble sheet singularity? Okay, multiple one bubble sheet singularity, and would the diameter uniformly bounded up to the first singular time? And the last question is, could we generalize this to the Ricci flow setting or more general ambient manifold setting, like Choi and Mandolidis, and they studied this in basically they studied the case of when the unstable mode or positive mode dominant, but the neutral mode is dominant case is, I mean, no, yeah. Yeah, thank you very much.
Also,